Yeah, today we're just going to go over an overview of most work that I've done in the past couple of years, and then kind of, again, what I plan on finishing out in the rest of my PhD. So that said, it kind of does have a larger title, like a more all-encompassing title. We're going to be talking about flame-generated turbulence for flame acceleration, detonation initiation, and propagation. And then really quickly, just I would like to thank the Air Force Office of Scientific Research, National Science Foundation, and the American Chemical Society Petroleum Research Fund for funding the work that we've done over the past few years. So that said, just a quick background. I mean, I think we all kind of know what's going on. But detonations are a form of pressure-getting combustion, which is why we want to study them so badly. And they also are very difficult to study because they have a lot of turbulence compressibility effects. They're very three-dimensional and they're very unsteady. And then obviously they apply to RDEs, GDs, and then also catastrophic explosions. So in that case, we kind of want to prevent them and understand why they work to help mitigate them. And then also they can help us understand the origins of our universe, the different type of supernovas. Particularly in this one, I have the one with the binary star system, where the one star consumes the other and then it explodes very quickly. So we kind of know why we need detonations and why we want to study them. Again, there's a lot of things we don't really understand in them. The first one being is the DDT process. So a lot of the work I've done has revolved around the DDT process. And today we're going to take a closer look at 3 of those steps. The first one being the preconditioning, and then onset and propagation. However, as an overarching thought, DDT occurs when you have a deflagrated flame and it goes under turbulent flame acceleration until a hot spot forms, typically at least, and then the flame front will ignite to form a self-sustaining detonation wave. So on this slide here, I just have a really quick overview of that process. So as you can see, you have the ignition all the way at the beginning, and that's when you have a little deflagrated flame that's not really traveling very fast. And then it produces compression waves, and then you get shocks. When you get shocks, we'll talk about that as the preconditioning stage. And then once we have that hot spot, we'll talk about it as onset or initiation. And then last, we'll talk about propagation, which is where you have a self-sustaining detonation wave. And we kind of want to know why they self-sustain a little bit more. So that's the background that we're going to talk about on DDT. And then really quickly, this is going to be specific to just nomenclature that I talk about today. And for that, when I'm referring to a slow deflagration, I'm just talking about flames that are going slower than the speed of sound of the reactants. And then also flames that experience little to no compression ahead of the flame. So when it's pretty calm and nothing's really happening. And then when I talk about fast deflagrations, I'll mention flames where they have a normal shock, and the normal shock is producing compression behind the flame front or behind the shock and in front of the flame front. However, those flames are still traveling below the speed of sound of the products. So they're not moving super, super fast, but they are accelerating still. And then lastly, when I talk about choked flames, it's anything after the speed of sound of products has been exceeded, but below the CJ detonation velocity. So it's when we're seeing a lot of compressibility effects and a lot of things that are very close to the runaway mechanism. So that's an overview of just what, when I talk about different things today, that's what I'm referring to. So then on that, I mentioned the turbulent flame speed, and a lot of the work we've done has revolved around validating the turbulent flame speed. Prior to me working at our lab, the girl who worked before me, she worked a lot on this process as well. So this is kind of some of her work here that we've done in the past with Dr. Polanenko. And this is just kind of showing that when your turbulent flame speed, or the rate that the flame consumes the reactants, accelerates past the CJ deflagration criterion, which is defined as the speed of sound of the reactants divided by, or the products divided by the fluid expansion ratio, which would just be the pressure difference or the density difference between the reactants and products. So when it exceeds that speed, then you're kind of guaranteed to transition to a detonation shortly after. This was validated in both the simulations and our experiment. And so a lot of our work has just been continuing part of that and kind of trying to understand that better. So that's when we talk, that's going to be a big point of today, is the turbulent flame speed. And then really quickly, when we talk about detonations, we're going to talk about CJ properties, which are just the series of equations we use to define flame regimes. So a lot of them, we'll be talking about the upper CJ point because we'll be talking about the detonations. And then also we'll talk about detonation cells for a little bit. And then that's usually an idea of mixture regularity, but it also dictates a lot of parameters for how we design facilities. But it's just the print that's left behind hand. So we'll talk about cells at the end. That said, after a quick background, here's kind of our motivation and why we want to study these things. So for preconditioning, there's been some recent work that we've seen that has shown significant expansion in flame surface area. There's been a lot of flame wrinkling occurring with strong turbulence flame interactions. And then also we've noticed in previous work that there's been an increase in pressure directly ahead of the flame. So we want to know, are flame turbulence interactions the driving mechanisms of flame acceleration, and how is it causing flame acceleration? So why are we seeing flame acceleration in some cases, but not in others? And then next we want to go into onset. So we know that we need, in order to get onset, we need a large temperature and pressure gradient. And we also know that when there's shock collisions within your flame and shock, it amplifies the energy release on the flame front to help promote onset. But what is it precisely that's contributing to the onset, and how is that onset occurring and why? And lastly, when we talk about propagation, we want to kind of deduce if triple point collisions are purely responsible for detonation propagation, or is there something else going on, like the reaction behind the shock front, and kind of more details on those. So that's kind of what we're going to look at today. And this is all going to be done in the turbulent shock tube. This is just a rundown of the facility we use for our experiments, and it is a 45 millimeter square channel. Most of the time it is 45 millimeters in its entirety. Occasionally we will shrink it down to 5 millimeters in thickness. And when we do that, it is only in the test section portion, so it's not throughout the entirety of it. It's 1.5 meters long, and it has a little bit over 0.5 meter of turbulence generators. For our turbulence generators, we use perforated plates with a 52% blockage ratio, or 58% blockage ratio. And the goal of that is just when we push the flame through, it's going to help promote flame acceleration. And so we have 5 that are pretty evenly spaced, and then we have a 6th one right before the test section, just to ensure an even turbulence going into it ahead of the flame for the reactants. And then in our test section, most of the time in most configurations, we have 4 transducers. We have a 5th transducer right before the test section for triggering cameras and different diagnostics. And then in that test section, we have 100 millimeters of optical access to kind of get whatever we need. There's also a laser sheet port at the bottom, or glass at the bottom, so we can also get laser diagnostics. And then I guess going back to the turbulators, that's kind of shown on the bottom left. When initially characterizing the facility, we tried a plethora of things to try and get the biggest range of flame regimes that we could. So we found with only 4 plates, we could change the equivalence ratio significantly, and we would never actually get past the sonic velocity for the configuration we had set up. Obviously, if we would extend the length or change something else, then it would be a little bit different. So when we tried with 11 plates, we couldn't get slow flames. We could only get detonations or flames that were very close to detonations. So the 6 plates kind of allowed us to get slow flames, but also detonations, just by changing the equivalence ratio in the facility. And this initial testing was done with hydrogen and air, so there's no oxygen enrichment, and it's all at atmospheric pressure. But it allowed a pretty good variation of conditions to look at, which has really been helpful in the past few years, as we've tried to look more into detonations. So that's kind of a breakdown just of the facility that we use. And then for injection, this has been discussed a lot in literature, but for injection, for anything we're talking about today, we use hydrogen air for our gaseous mixtures. And I have the gaseous diagram on the bottom left. So for that, we regulate our gases to 50 psi and then put them through rotometers and mix them in polyurethane tubes. Total in mixing, we probably have about 0.5 meter in these tubes for promoting mixing, just to make sure we do have as pre-mixed of a mixture as possible going into the test section. And then when it actually enters the test section, it enters entirely around the spark plug. So we have 8 different ports, and they all kind of point towards the spark plug in the square direction. And then when we use hydrogen, we talk about equivalence ratios, it'll be anywhere from 0.7 to 1.2 with a detonation velocity around 1950 meters per second. And then for some of these tests, we do talk about vaporized liquids. So we used 1 micron droplets in a control volume mixing chamber that you can see on the bottom right. And basically we inject them at the top of the injection port and then kind of run air through to help mix the gases together. So in this case, we use pure oxygen. And then the oxygen goes, and the oxygen and the fuel go into the test section just through one port to help prevent the gases from, or the gases from returning to liquids again. And so then we go into the test section. And then for that one, we do use a pre-detonator. It's just a 1 foot Schelken spiral instead of a spark plug. And that's just to get a little bit more activation energy because the atomized fuels we found were a little bit harder to ignite. So that's kind of why we see the pre-detonator there, but not in the other configurations. And that's how we inject most of our fueling. And then really quickly, just the diagnostics we'll talk about today. So as an overview, we, in the preconditioning regime, we use chemiluminescence, pressure measurement, Schlieren, and PIV. And this is an overview of the setup that we used. So we used 2 SAZs and an evergreen at 50 kilohertz. And then we have everything set up in a configuration that reduces angles as much as possible. Obviously, we can't make all of them go away, but we do get most of them to be minimized at least. And then we use an SA1 for chemiluminescence. So that's kind of an idea of how we get our preconditioning diagnostics. And then here's a little bit more of the specifics on it. So we take PIV, like I said, at 50 kilohertz. It is frame straddled PIV, and that's just so we can get a little bit faster. And we use 30 nanometer aluminum oxide seating. There was a study done with Damati and some of the students that used to be in our lab as well that kind of found that if we were at a low enough size of seating that we were able to get really accurate measurements and we were able to track the flow very well for the high speed flows. And then we use a 2-step multi-pass method with 75% overlap to just try and capture as much as the vectors we can and get a more accurate reading. For these preconditioning measurements that were all done simultaneously, the Schlieren was then also at 100 kilohertz. So our PIV and our Schlieren are recording at the same rate. And we get pretty good spatial uncertainty with both the Schlieren and the chemiluminescence. Chemiluminescence was taken on the SA1, so it was a little bit lower and didn't quite have as high a spatial resolution, but it was still pretty decent. And then our pressure measurements, like I said, we have 5 transducers, the one before the facility, and then we have the 4 during the facility, and they're 25 millimeters apart, and they record at 1.25 megahertz. So we're able to get really accurate data from those as well. And then here's an overview of our setup on the right, and also some views of our chemiluminescence imaging. In it, we will show filtered chemiluminescence images, and it's just a color filter. It's not, they are black and white filters when recorded by the camera. And then when we talk about onset and propagation, we are using ultra high speed Schlerens. We're using a Hadlin-Shimatsu that's recording at 5 megahertz. That said, it does have a very high pixel-based uncertainty just because it is recording so fast and its resolution is a set resolution. And then when we take our chemiluminescence data with that, for the cases shown today, we are using an SAZ at 400 kilohertz. And again, when we use the pressure measurements, they're still at the 1.25 megahertz. And then down at the bottom, I just have a video of a 1 megahertz detonation. It's not indicative of anything. But that's kind of the setup we use for those. So then now that we know what setup we use, here is a little bit more insight into our testing conditions. So for these slow deflagration cases that we'll talk about today, it's when our turbulent flame speed is propagating below our CJ detonation velocity, or not CJ, sorry, CJ deflagration velocity. We are at an equivalence ratio of 0.84, and we're at about half of CJ, a little bit less. And our turbulence measurements are about, our U prime measurements are about 42 meters per second. So we see some variation in turbulence, but not a ton. I think here you'll see the shock. So it is a little bit faster in the slow deflagration because there is a shock, but there's very little compression between the shock and the flame. So that's kind of what our slow deflagration looks like when we talk about it today. And then when we talk about our fast deflagration, we are getting closer to a stoichiometric picture, but we're still a little bit lean. And we're also seeing over 50% CJ and a little bit higher turbulence at 70 meters per second. And here our turbulent flame speed is close to our CJ deflagration speed. So it's not always exactly at it, but it is in the same ballpark. And as you can see on the Voorhees diagram below, it's a little bit higher in turbulence. And then here's our fast deflagration. So our shock and flame are a lot more coupled. And then you can see a little bit more compression happening on the flame front, and we'll go into more of that in a second. And then the last thing we'll talk about that we actually have turbulence measurements for will be the choked flame. And like I said, we're talking about this when our flame speed is moving faster than our speed of sound of our products. And we see a lot higher U prime measurements at about 109 meters per second. We're also right under CJ for pressurized, so we're at 0.99. And then our equivalence ratio is getting closer to stoichiometric. And lastly, we talk about detonation. We don't have turbulence measurements for this because we have not done PIV on detonations because 50 kilohertz is just a little bit too slow to actually capture what's happening, and it wouldn't really provide accurate readings. So then that's our detonation case. And it's moving at a CJ velocity and CJ pressure. And yeah, so that's kind of what we're going to be looking at as far as test conditions today. That said, going into the results, this is the results from our preconditioning test. So for this, we wanted to, when we were talking about preconditioning, and we wanted to better understand the subset of flames to get to a initiation point, we wanted to really know the differences between each of those regimes going up to that. So the slow deflagration, the fast deflagration, and then the choked flame. And so the first thing we wanted to do is, as we were seeing these pressure measurements increase ahead of the flame in choked flames, or right before we would transition to a detonation, we wanted to understand the compression coming off of them and how that would play a factor into the results that we were actually seeing, and if we could tie those together. So in what we're calling the slow deflagration today, in this image here at the bottom left, we have our Schlerin imaging with our X over H, H being the characteristic height of the facility. So that would be the 45 millimeters, and X being just the distance that we're traveling divided by that. So it's all normalized here based on the shock position. So it's how far our flame is still from the shock. And so here we have our shock, and our flame is about 4 X over H distances behind our shock. And in that, we see pretty steady compression in between the shock and the flame. So we're not really seeing any large bands or any super strong gradients qualitatively. And then in our pressure traces on the right, we have, again, X over H. You can see our pressure traces are seeing about the same values that our shock and our flame are that distance apart. And then I've also labeled the time because I think that also gives a good perspective into how much time we're actually waiting until we see these two different events. So our shock comes in at X over H is 0 again, and then we see a little bit compression building to about 0.2 CJ in this exact case. And finally, when we get to the flame, it takes 296 microseconds. They're very separated temporally, and we don't really see any strong gradients between the shock and the flame. It's just kind of a steady band of compression going up. And then when we got into our fast deflagrations, first thing we notice is that the shock and the flame are a lot closer. And we start to see these smaller bands of compression that are a little bit more heightened. So it's a largely black background. And then we have these little stronger bands of white versus just like a steady color. And then that's evident here also in the pressure. So you can see the shock coming in a little bit higher, and then downstream, you can see the pressure increase pretty strongly before the flame comes in 146 microseconds later. And then on our choked flame, so you see the shock and the flame, and they're very closely coupled. So they're only about 50 millimeters apart. And temporally, they're only about 36 microseconds apart. And you see the strong white band forming ahead of the flame front. So we see a lot of compression coming off of the flame. If you notice, it kind of initially matches the shape of the flame. So that's a lot of what motivated the study, is we were seeing these really strong compression bands almost emitting from the flame front that we wanted to understand better. So here we have our shock coming in, and then we see a ton of pressure increase right before our flame comes in 36 microseconds. So qualitatively from our slur, and that's kind of what we're seeing, and then also our pressure measurements were showing these really high increases in pressure right ahead of the flame front for flames that were approaching the CJ deflagration condition. So in going from that, we wanted to look more into the PIV characteristics and flow fields that we were seeing to see if those were matching or giving any more insight into this propagation theory, phenomenon that we were seeing. So just taking a look at the velocity measurements from the PIV, here are some of the results from that. So we have our slow deflagration. And like I said, they're about 4 x/h apart. In the PIV, we were reading about 3.8. And then in here, you can kind of see, which we'll go into a second, but the velocity doesn't change a lot of the gas between the products and the reactants. So there's not a lot of compression going on in that. There's not a lot of like variation happening. And so in our fast deflagration on the right, we can see that our shock and flame are a little bit more coupled. So the PIV for this case was reading about 3 x/h apart. And then here we're starting to see a difference between the gas velocity of the reactants and the products. So we see an increase in our products, which we don't really see for the slow deflagration. And then in that, it's kind of a good hint that we might be seeing a little more vorticity production as well. And then finally, in the choked flame, they're still very close apart. And notably in this one, we see a very flat flame. So while they were more wrinkled in the slow deflagration and the fast deflagration, the choked flame seems to have little variations, but globally it's pretty uniform in a flat line. And then we see a lot of variation between the reactants and products as far as velocity goes. But then also in the reactants, we see these hotspots of very increased velocity, probably due to decompression and ideally vorticity. So then going into that, we went and looked at the actual vorticity measurements for each flame. And here in the image before, we are looking at a y/h of -0.25 to positive 2.25. So we're looking at a pretty wide range and a pretty like global view of the flame. And then when we're looking at these vorticity measurements in this one, we are a lot smaller. So we're looking at about half the field of view here, just to get an idea on local vorticity measurements. And so what we found is that vorticity magnitude is increasing locally with increasing flame regimes, which is then resulting in a higher turbulent compressed region for the choked flames. So in that, we kind of found that there was this coupling between turbulence and pressure in the compressed region. And eventually we believe that that's going to lead in some sort of baroclinic torque production. But here we just have the U velocity on the top. So that, like we saw before, just at a localized, a more local field of view. And then on the bottom, we have vorticity. And for that, for the slow deflagration, we see kind of even vorticity throughout the reactants and products. So there's not really any, they are like positive and negative, but there's not really any stronger levels in the reactants and the products. It's pretty uniform. And if there wasn't a flame front there, you probably wouldn't really know where anything was. And then in the fast deflagration, we see a little bit stronger vorticity in the reactants than the products, but again, it's not super significant. We just have a little bit stronger bands there. And then finally, when we get into the choked flame, we see a lot of variation in the vorticity in front of the flame. So in the reactants region, and then the products, we don't really, it kind of dies out and goes back to like a more nominal turbulence changes. And so with that one, we can kind of pretty clearly see where the flame is from the vorticity alone, which means that ahead of that flame for these choke cases, we are seeing a lot of vorticity production between the shock and the flame, which is likely heating up our compressed region, making it ideal for a hotspot to form. So then going into that, those turbulent fluctuations a little bit more. For these cases, it is pretty important to note that we are taking PIV at 50 kilohertz. And so we are getting a few frames of these images, and we do repeat a lot of them to make sure that we are seeing the same thing every time and getting similar values every time. That we aren't able to take temporal averages because we don't temporally have a ton of frames to work with to keep our resolution high, everything like that. So we take our local turbulent velocity fluctuations as a spatial grid instead of a temporal grid. So we're not looking at anything over time. And we are looking at it in 4x4 grids throughout the flow field, but it's not temporal. So just to preface that, so when we get our fluctuations, we're looking at a 4x4 grid and saying, okay, compared to the average of this is how much turbulent fluctuations we're seeing within that grid. And it's been validated, and we've used it a few different times in other works, and it's shown to prove pretty good results. And then this is our calculation. Here's our equation on how we actually do it. So then for this, we wanted to compare the local turbulent velocity fluctuations for each regime. So starting at the slow deflagration, we took 4 different flow field regions, and we marked them here as flow field regions to better understand spatially what we're looking at. So then shock 1, or like the first region, will be the shock, and that will be the point 1, and then point 2 is going to be the reactant. So that's going to be some area between the shock and the flame that is far enough from either that we'd be getting a pretty good result of what's happening between the two. Obviously for the choked flame case, as you can see, the shock and flame are very close together. So they are like not spatially as far apart as the slow and fast deflagration, but we still are just getting reactants for that measurement. And then we have 1 at the flame. So this is taking about 5 pixels or 5 grid counts behind the flame and then 5 grid counts in front of the flame. So we're getting an idea of what's happening right at the flame front. And then in the products, it's just a little bit downstream. So it's another box that we use as well. So in this, we can see starting out between our slow deflagration, fast deflagration, and choked flame, the choked flame automatically has more turbulence behind the flame front, or more velocity fluctuations behind the flame front. And then as we go into our reactants, we see the fast deflagration case we use actually sees a slight decrease in local turbulent velocity fluctuations, and the slow deflagration just kind of stays stagnant most of the time. But then when we get in this choked flame case, we see a really large increase in the reactants, and then we see an even higher increase at the flame front. And that's more so attributing to this idea or notion of this flame generating turbulence and generating compression waves into the shock. Whereas with the fast deflagration, when our CJ speed is not exceeded, and when we are not seeing a ton of increased pressure in front of the flame front or a ton of compression bands emitting from the flame, everything just kind of stays stagnant as well. And then again, with our choked flame case, as you can see, we see a little bit of a decrease at the end. And that's just likely because it's burnt products. So it's just kind of a little more stagnant than both the reactants, where it's super high in vorticity, and then also at the flame front. So that's kind of some of the results we're seeing from our preconditioning study. And then here, this is lastly just going into the turbulent flame speed. This is a very rough PDF, so we can't make a lot smoother PDFs. But like I said before, the turbulent flame speed is just the speed of the flame minus the speed of the gas. And our flame front is measured from the chemiluminescence measurements to get the most accurate reading of the flame front. And then our gas is collected from a box region directly ahead of the flame front. So the moment that we are not seeing flame, we kind of make it in a square box or a rectangular box, and then that's where we're getting our gas velocity from. And then for our turbulent flame speeds results, obviously the slow deflagration is moving very far below SCJ, which for hydrogen air flames that we use, it's about 292 meters per second. Obviously there is some variation with the equivalence ratio, but it's not super large, and it's not very drastic or driving for these flames. And so for that, our slow deflagration is maybe 110 meters per second. So it's very far below that. And then our fast deflagration is almost at that velocity, but still moving slightly below it, or seeing a slightly less ST at 280 meters per second. And then for our choked flame, when we're really close to our SCJ, or really close to our runaway mechanism, we're at 700 meters per second for turbulent flame speed. So we know there that we are getting a lot closer to actually transitioning to a detonation. And then with that also, if we notice the distribution, they kind of spread out with each increasing regime, and that's just attributed to higher heat release levels. We'll do more study on that later, but for now, that's kind of what we've deduced as far as the distribution in the higher SCJs. And then going on to just a discussion on that, and as kind of a whole thought, is we were able to experimentally alter the equivalence ratio to study flame-sparing heat release. So then in the flames with stronger heat release, we were able to see misaligned pressure and density gradients, and that's shown at the beginning. And then through that, we see higher PIV vorticity fields and higher U prime, so that would be attributing to turbulence production. And then finally, in the end, we see this flame acceleration from this increased turbulence production. And so we kind of think of that as a cycle. So the more heat release we have, the more misaligned we are, the more turbulence we produce, the faster our flame goes. And eventually we would kind of go through that cycle until we get to DDT. And currently we want to think that that has to do with baroclinic torque production at the flame front. However, further investigations are going to be required to understand that a little bit better. So that's a lot of the work we've done to actually get to a detonation. And this is published in the proceedings from the last symposium. And then going into that, we wanted to look at detonation onset. So a little bit, once we've reached the preconditioning and start to exceed that, we get onset. And we first wanted to look at this as a global thought. So we did 3 windows of our facility. So like I said, we have that 100 millimeter long test sections. We just have 3 of those in this case, and they are running simultaneously. And we're able to rerun these images to get an idea of what's happening and how we're seeing this global onset. So here in the first window, we see a shock flame complex. And then over 60 seconds at the end, we see a detonation. These images are taken at 100 kilohertz. So like I said, there's no local resolution in this image, but it does give a pretty good idea of what's happening. So we see the shock flame complex come in, and then at 30 seconds, we see there's not a big band or difference between the shock and the flame, just qualitatively in the Schlieren. And then at 40 microseconds, we see this really bright spot. And due to the exposure and the frame rate, it's likely indicative of a hot spot forming somewhere between the flame and the shock. It can't be wholly reduced because of both our resolution and our speed at this point. But then by 50 and 60 microseconds, we see a pretty steady propagating detonation. It is overdriven for a little bit, so it is moving a little bit faster than the CJ velocity, but then it does eventually settle down. There's a third window that we do have that shows this detonation propagation a little bit more. But the first 60 microseconds is where we really see the transition period. And something we note in this period is, like in the preconditioning, immediately prior to onset, the shock and flame are separated. So here on the left, we have both our velocity evolution and our shock flame separation. So this is measuring the distance between the shock and the flame up until up throughout the entire event. So this data does take in the third window into account. So velocity, we see our shock and flame moving about 70% CJ. And then when DDT initiates at 40 microseconds, we see a super high overdriven velocity. And these are shock velocities that we're taking, just to clarify. At 40 microseconds, we see a super high increase in detonation wave speed. And then we see it kind of settle down to CJ as the detonation propagates. And then again, in the shock flame separation, we see our shock and our flame are kind of moving steadily distance-wise from each other. And then right when they have this explosion, we see the global flame front kind of back a little bit more. So it's a little bit more separate from the shock. And then at 50 microseconds, they start to couple and propagate uniformly throughout the flow. So that's a global onset transition. And so from that, we wanted to understand locally more what was happening. So then we switched over to our high-speed cameras so we could look at detonation onset a little bit better. So in this camera, really quickly, the field of view is about 65 millimeters wide by 45 millimeters tall. And this is where we have our Shimatsu running at 5 megahertz to capture this event. And then also we have our SAZ running at 400 kilohertz. So on the right, as you can see, we have both images laid next to each other. And then the SAZ is a little bit less time resolved. So we do some, we kind of match where we're at temporally with the images to get those two. And then we have our velocity throughout just tracked really quickly. And as we can see, that starts below CJ and then eventually increases past DCJ. And downstream, I'm sure it would settle back. And then when I play the video, you'll see this hotspot expansion. And in that, I just have a trace of the flame front to see how it's expanding over time. So I'll go ahead and play this video. I'll play it a few times. As you can see from the images on the right, the hotspot does happen at the very bottom of the window, and then it will expand throughout it. So we'll play it probably like 3 times. But you can see down at the bottom here how it starts to expand and come up. And then through that, we start to see this cellular detonation front all the way on the right. And as it propagates out of the flame. So I'll play that one more time. And again, it'll be like right here. We see it coming up, and as it comes up, you can kind of see how much faster it's moving relative to the rest of the flow, which I think is really neat. And then it propagates out of the flame. So that was some of our work on detonation onset. And we are looking a little bit more into that, but it is a very hard problem to look at. Just understanding these hotspots and getting them captured in the right spot, as they can happen anywhere throughout the flow. So they can happen in the middle, they can happen at the top, they can happen at the bottom. We just have to be capturing the right image at the right time. So then finally going into propagation. So part of our understanding of propagation is wanting to know more what's happening on the cellular front of the detonation. So we're looking at these hotspot ignitions. We also were seeing some detonation cases where we're seeing this really strong reaction happening. And then this data that I'm about to show here is taken from a 45mm square channel. So we are taking up to 3 detonation cells propagating in line of sight imaging. And I have this DNS on the right here from Jackson Crane last year. And this is mainly just to show that there can be multiple fronts at varying stages throughout the detonation channel. So in Schlieren, we know we're getting line of sight imaging, but this kind of gives, in my opinion, a pretty good overview of seeing what that line of sight is. So this is not representative of our mixture or our study. This is just a detonation propagating in a square channel that has varying fronts at varying parts of the detonation cell. So I'll play ours here. So we're able to see a really strong triple point collision, and that's likely due to having such a 3-dimensional flow. And then you see this like kind of intense reaction collisions as well when we play this. So as we come here, we see these 2 shocks come and then they expand, and then we see another set of shocks come and expand as well. And like I said, this is line of sight imaging, so we are integrating across 45mm of our section. And so then we wanted to be able to isolate this a little bit more. So then going into that, we first did look at chemie, and here's the chemie and how they expand. And the other thing we were noting here before we get to the isolation is that when we were seeing this jet, we were seeing this insanely high velocity. And at this point, we did have pretty significant uncertainty in our velocity measurements. So we wanted to repeat this and see if we were getting these super high velocities as well. Specifically, we were seeing these 2 shocks collide in this like strong chemiluminescence form. So then we went and we repeated this with the liquid fuels. So this is all in the square channel, but this is RP2 and JP10 with the chemiluminescence overlays. And kind of we were seeing the same thing. So whenever we had these jets, we were seeing this super high velocity. In the case of the liquid hydrocarbons, we were seeing about 3,500. And in the case of the hydrogen air, we were seeing about 5,500. Like I said, this was 3-dimensional. So when we were seeing this, this likely was more than just 2 shocks colliding. This is likely like 3 or 4 shocks colliding at once. But every time we saw these collisions, we saw this really bright band of chemiluminescence and then a very high detonation CJ velocity, about 2.5 times. And then also it was an amplified version of blast decay theory, which made it a little more interesting because we were seeing much more than we were expecting to see. So then from that, we went and closed it into a 2D channel. So our quasi 2D is 5mm thick. Our hydrogen air cells at stoichiometric supposed to be at 15mm, and then at a lean equivalence ratio, it should be about 25. We measure ours usually around 17mm, so we are slightly smaller on that side. But with that, the 5mm thick being very small relative to the detonation cell, which being about 1/3, it does cancel out a lot of those 3-dimensional effects. And here in our shadowgraph imaging, we're able to see a lot more clearly what's happening. So we have our 2 impinging waves happening at frame B on the right, and our incident shock, and then our waves collide, and then we have this gas push forward, and then it expands, and then we have more collisions. So we're starting to see the good idea of what's happening throughout our detonation cell. And then kind of here, I think we've shown this in a couple different things, but then this part is unpublished, but this part is going into more of a detonation cell cycle. So we have our cell expand or collide and expand, and we're able to see our chemiluminescence behind it and track that pretty well. And so we believe here that the triple point collisions are assisting it in compressing gas, but then the gas igniting and pushing the strong reacting jet forward and making this new MOXDEM is doing a lot of the work in detonation cell propagating, and why we see propagating detonations so easily. So I'm looking a little bit more into that. As we track the shock and flame throughout the cell, we see that our gas velocity initially exceeds as our jet ignites, and then it decreases as our shock and flame start to separate. So here on the bottom left, it is a kind of broad inference on convective gas velocity. So it is not measured from PIV, it is measured from chemiluminescence using PIV processing. So it is not exact, but it is deducing a lot closer to what we would expect a gas velocity to be. And farther work will go on to show if we can actually track that velocity with megahertz PIV. And then in the two middle here, we just have a shadow graph and chemiluminescence data of the same occurrence, so it's simultaneous. And then on the right, we have this detonation cell cycle and these regions. And these regions are just taken to kind of show at the same location or at the same point in the cell where velocities are, with the gas velocity being measured. Here it's just being measured from the front, so it's just the same way we measure Schlieren, just using it with the gas. So it's not, it can have higher accuracy, and we're getting it to be there, but it's kind of what we're seeing now. So in this 2D channel, we go back down to the about 1.4 DCJ, which is what we see typically in blast decay theory. And we're able to see here that throughout the cell, we do see this decay. And then additionally, on top of that, throughout the cell, also noted in the points of collection that we have on the top right, that initially our shock and flame start out really, really close together. And then throughout the detonation cell cycle, they seem to spread apart and get much further apart. And then in case 5 and 6, as you can tell, we barely even really see that reaction zone. So there's no reacting going on there. But then in case 7, they collide again, and then we see this reaction zone pick back up. So likely we're just compressing the gas and then igniting it. So we're trying to do more work to understand that ignition process for that. But those are kind of where we're seeing as far as detonation propagation goes. So as a quick discussion of that, we're able to see onset after we have a lot of flame acceleration, where the shock and flame couple and then begin to propagate together. And then propagation is sustained through a cycle of instant shock collisions that produce local chemical explosions that expand and contract, forming detonation cells. And that's seen in our propagation studies, where for the 3D propagation, we have multiple cells propagating in both directions, allowing for a lot stronger and faster jets. And we know that liquids and gases are experiencing similar processes. So it is confirmed that this mechanism is universal for these regular cells. And then when we go to the 2D channel, we're able to see that the front structure is more apparent. And local velocities are fluctuating between 8 and 1.5 DCJ. That it's a process of collisions, expansions, and reflections. So that's what we're seeing as far as onset and propagation. And then as a quick conclusion of the entirety overview process, first we started out by experimentally characterizing flame turbulence interactions at varying levels of heat release to deduce flame acceleration as a result of turbulence production from misaligned gradients. And we can see a video of that on the right. And this is some of the Shimatsu data we've taken. So it's just a good overview of what's happening. And then in the middle here, we witnessed increased separation between the shock and the flame immediately prior to onset. And locally, with respect to the hot cell, we saw pretty good expansion. So here's that video just playing there, and then you can see the shock flame separation over time. And then last but not least, we looked at detonation propagation with various fuels and channel configurations to explore the cyclic process of shock collisions producing these chemical reactions. So we have this Schlieren video playing here, and then the regions that we discussed as well. And lastly, going on to future work. So this is kind of what we are currently working on and haven't really rounded out yet. We want to compare all the data we've taken with the hydrogen air flames with hydrocarbons in the same facility. So we, in this image, are showing methane and propane, but we've also done ethylene. So we can kind of get an idea of this runaway process and this CJ deflagration speed from various hydrocarbons, while also looking at detonation onset for these hydrocarbons using faster imaging. But this is just a global study on different hydrocarbons in comparison to hydrogen under the same boundary conditions, so using the same facility and just changing the mixture going into it. Recently, I've also done a little bit of work onto detonations and droplets, and how droplet sprays and atomized liquids can affect propagation. So here's two videos here, one of them of a detonation and one of them of a shock, and just kind of what they see over time. So this is a newer study that I'm just helping out on, but it has been pretty fun. And then last but not least, we want to do hot spot production and temporal detonation characteristics through megahertz laser diagnostics. So this is just a Schlerin image, but we plan on using a pulse burst mode laser to help better understand detonation propagation. So that's all I have today. And thank you for listening to me talk. If you have any questions, please let me know.
Thank you very much for your talk, Rachel. I appreciate the picture on the right side there. It's a nice combination of like a Schlerin shadow graph with the chemiluminescence. That's really nice to see.
Thank you.
Yeah, if you have any questions, please put them in the chat or raise your hand. And I see we have a question from Sai Sandeep Damati. If you want to ask it yourself, please.
Yeah. Hey, Rachel, interesting experimental work. Can you go to slide number 5, please?
Yeah.
When you classify these into slow deflagrations and fast deflagrations, I'm a bit confused here. Can you tell me what is the range of the flame mark number in the case of slow deflagrations and fast deflagrations, meaning that what is the reaction wave speed compared to the speed of sound in the reactants?
So for the slow deflagrations, it would be the flames would be propagating, or the flames would be not the turbulent flame speed, but the flame speed themselves. So just like movement of the flame, not in respect to how it's consuming the reactants. Those are propagating slower than the speed of sound of the reactants. So most of the time there's no shock present. Sometimes there is, but that's kind of when you're getting on the border of the two, which is where we look at. But it's just anything in my work, at least when we're talking about it, when I talk about slow deflagration, I'm just talking about any flame that's moving slower than the speed of sound of the reactants. Whereas fast deflagrations are moving above the speed of sound of the reactants, but below the speed of sound of the products. So I believe for hydrogen air, the slow deflagrations are moving between like 0 and 355 meters per second. Maybe it's 390, but they're moving less than 400 meters per second. And then the fast deflagrations would be anything moving between, I think, 400 meters per second and 1,000 meters per second. Again, this is just the like reference, like looking one frame to another and seeing how fast it's moving, not the consumption rate. And then the choke flames are anything from the speed of sound of the products, so 1,000 meters per second to the CJ detonation velocity.
Okay. So in case of fast deflagrations, do you say that it has to be greater than the speed of sound in the reactants, or can it be a factor less than the speed of sound in the reactants, but still it shows compressibility?
I would say that the bottom limit would be more of a gray area, so it does show compressibility, but it could be around the speed of sound of the reactants. In general, we don't, our experiments at least don't see a lot of compressibility in slow deflagrations. We see some, but it's not large.
Okay. Can you go to the next slide?
Yeah.
So here you call SCJ as speed of sound in reactants divided by the fluid expansion ratio.
Yes.
Is that correct? Usually CJ speed is the speed of sound in products.
Yes, yeah, that was more of a typo than anything. I know there's not a strong difference between the two, but yeah, it's supposed to be products, not reactants.
Yeah, okay. Okay, we are on the same page then.
Yeah.
Then can you go to slide 24? Okay, just go one slide back, sorry. Here on the, you characterize the URMS of the fluctuations. So what this is essentially saying is that you have turbulence generation near the flame front and nothing ahead in the reactants and the shock. Is that correct?
Yeah, so we see more turbulence generation in the flame or ahead of the flame front.
And what happens to the turbulence in time? Does it propagate into the towards the flame, towards the products, or towards the reactants? It should be towards the reactants, right?
So we don't have temporal measurements for this. We don't have temporal measurements at the current moment, just because our PIV was at 50 kilohertz, so it wasn't quite fast enough to actually get a good idea of what was happening over time.
Mm-hmm. Okay. And the decrease in the URMS from flame front to the products is just due to viscous dissipation?
Likely, yes. Yeah, we just in that case, we just don't see as much turbulence fluctuation in our products.
Okay. Can you go to, so in case of the choke flame, you say that the speed of the reaction wave is greater than SCJ, but it doesn't undergo DDT. That's what you call as choke flame, right?
Yes.
Why doesn't it, the runaway process has started, but it doesn't undergo DDT? Why is that? Is your tube small, or if I run it for longer, does it detonate?
It probably does. So if we look, here, it probably does undergo DDT. It would just end up being about right here. So when we increase our equivalence ratio, if we want to see DDT, we need to be a little bit closer to 1. So in that case, I believe we're at 0.96. And usually we see transition in this window at about 0.98 and 0.99, or like between 0.96 and 1. So likely we were very close to it DDTing, it just wasn't quite there yet. So if we would have either increased our equivalence ratio just a tad more, or if we would have looked just a little bit further downstream, then we would have seen the transition happen. Because at that point, the runaway process had happened. It just hadn't transitioned yet. It was just a matter of time before it did transition.
So that suggests that there is some intrinsic time scale, right, for which the DDT would happen. Like, it's not sufficient that the flame speed exceeds SCJ. It has to, there is a time scale of it takes for it to undergo DDT. Did you get a chance to look at, like, what's the time scale like?
We are currently looking into that, but we haven't quite resolved a time scale for that yet.
Okay. Can you go to slide number 25? Or the slide where you show the vorticity fields between different flows. Yeah, one step back, sorry. One step back, maybe one more. Yeah, this one. You show there is vorticity generation, right? Did you try to characterize the turbulence or the velocity field that you're seeing as I go from left to right? Like, how different is the turbulence? Is it more anisotropic? What kind of turbulence is it? Is it like Kolmogorov type turbulence? Did you have a chance to characterize it like that?
For the slow and fast deflagrations, it shows to be pretty isotropic. So we see pretty even U prime and V primes. I'm not sure for the choked flame, just because we were so close to DDT, if it would be perfect. But the facility is designed to experience isotropic turbulence. So overall, in the reactants, we would have had pretty steady U prime and V prime.
So you have, it's 3D, right? So you have U prime, V prime, and W prime. So all three are, you're saying it's isotropic, like it doesn't matter which direction I'm looking at in terms of this flame generated turbulence.
It should, yes. We cannot calculate the third dimension just because it's PIV, it's 2D. So we do have a 3D channel, but we don't experimentally have not calculated the third dimension. Likely it would be yes, but we'd have to do further studies to actually prove that.
So my last question is, how universal are these results? Let's say is it dependent on like the system size, the turbulence intensity, or is there like a minimum turbulence intensity and box size or the system size that I need to see such results?
So we've currently repeated this for other fuels. So we've repeated it for methane, ethylene, and propane. And we are seeing similar results as far as system size goes. We currently have only done these tests on one system. So again, we would probably have to look more into it. Likely it is a universal concept and it should be able to be repeatable at different systems. But this experiment was done just on a singular facility. So likely, yes, and we see similar mechanisms in other fuels, which would indicate that we would see the similar process, but it is all done on the turbulent shock tube.
Okay, thanks.
No problem.
Yeah, thank you for your many questions. On the time scale of DDT, I know that in our participant list today, we have a lot of people who've been working on this, and getting the exact time scale for DDT is pretty difficult, and you have to look over, maybe a few meters or more. So that can be hard. Yeah. So again, thank you for your questions. If there's anyone who wants to add to that, please raise your hand or write something in the chat. While we wait for those, I was wondering, Rachel, how do you seed your PIV, and what do you seed it with?
So we use aluminum oxide particles. In this study, we use 30 nanometer for the size, so it could be as small as possible with still getting a good resolution. And then we seed it in a tube, and we put both the fuel and the air through it, so it is ideally as pre-mixed into the flow as possible. It has a couple different grates that it goes through to help make sure it's not conglomerating or like building any weird flow structures in it. But we just seed it through our filling process, so it's seeded with the gas as it goes into the facility.
Okay, and have you seen any effects of how it affects the flow, through heat transfer and drag?
So from the perspective of data that we take with seed and without seed, so I guess chemiluminescence and Schlieren, our chemiluminescence results in the same flame speed with or without seeding, and our Schlieren qualitatively appears to be the same. Obviously Schleren's a little more qualitative, so I say that with a grain of salt, but our chemiluminescence matches very well, and we don't really see any difference in like intensity or in flame structure or in velocity or anything like that. So because our particles are so small, likely we are capturing the actual flow field and we're not getting a ton of drag effects. Yeah.
And do you have an idea of the particle concentration in the?
I haven't calculated it, but when we look at it, it is like when we look at a like raw image, it is pretty like dense. We are seeing a decent number of particles. It's not sparse, and our correlation values, I think, for the slow deflagration case are, I believe, like 0.7. So we are seeing really good agreements on like the -1 to 1. So we are likely seeded well enough. Our seed density is good because we are seeing good correlation, but I don't have a calculation that's actually calculated how much seed we have in the facility.
Oh, that's okay. Yeah, thanks a lot. Are there any other questions from the chat or from the audience? I don't see any in the chat. If not, thank you very much, Rachel, for your presentation again. And I'd like to apologize to anyone in the audience who's joining us late, because we did have a mix-up in our times. There's the possibility of another mix-up in times just 2 weeks from now when the Europeans changed to their daylight savings time. So just double check that. So again, sorry if there was any mix-up and you've arrived late. We'll put this presentation online so you can catch up on what you've missed. Rachel, thank you very much. As I mentioned, Rachel is I'm a new member of the organizing committee for the Young Researchers Forum, so you'll be seeing her more hosting some of the future talks. So thank you very much, everyone, and have a nice day.
Thank you.